we're going to learn about acids and bases, some of the theory behind them, and also some acid-base calculations. You should have learned a little bit about acids and bases last year in grade 10, so the first little bit might be some review, but hopefully that helps you remember some of the content you've already learned. So what we're going to start off with is comparing some properties of acids and bases, how they might be similar or different. So in terms of taste, if you were to taste an acid versus a base, acids have more sour tastes where bases have a bitter taste. So the difference between the two examples with acids are something like a citrus fruit, like an orange or a lemon or a lime. You bite into that and you get that soury taste. Bitter is a little bit different. Bitter, a good example would be if you've ever got soap in your mouth. Soaps are basic. If you've tried tonic water before, tonic water has a bitter taste. So those are some common examples of bases you might have encountered in your daily lives. Next would be feel. So if you're able to feel them on your hands, what would they feel like? Obviously, this isn't recommended if you're dealing with acids and bases in the lab, but if you were thinking about acids and bases that you encounter in your daily lives, these are some things you could think about. So acids have a similar feel to water. If you had lime juice or lemon juice on your hands, it feels similar to water. But bases are distinctively slippery. So soap is a perfect example of this. Any products with soap in them, they're basic, and you can feel that they slide, they glide on your hands when you wash your hands, and that's that slippery feeling. Acids and bases both have to be dissolved in water, and if you check their conductivity, they're both conductive when dissolved in water. Now, what happens when they react with different things? If you place a metal with an acid, you're going to produce hydrogen gas. So we did this before back in Unit 2, when you have magnesium in hydrochloric acid, for example, it bubbles and produces gas. Whereas if you put metals with a base, there's no reaction, NR. What happens if you put compounds that contain the carbonate ion and mix them with an acid? These ones also react and you get carbon dioxide gas, but with bases there's no reaction with carbonates. Carbonates tend to be basic, so that would be like putting two bases together, which doesn't really make too much sense. Next, we've got the ammonium ion. So the ammonium ion, any compound containing that ion, it's actually an acidic ion. So the reason why it doesn't react with acids is you would be putting two acids together. But if you have the ammonium ion and mix it with a base, you actually produce ammonia gas, NH3 gas. This is toxic gas, stuff that you don't want to breathe in. Then we'll take a look at a few indicators. There are more indicators for looking at acids and bases than these two, but these are common ones you might have seen. So litmus, like litmus paper, there's red litmus paper or blue litmus paper. In either case, acids will make those paper either stay red or turn red, but bases will make them turn blue or stay blue. A common indicator that we use in chemistry is one called phenolphthalein. In an acid, it has no color, but in a base, it goes a bright magenta pink color. So these are some typical characteristics and properties of acids and bases that hopefully you learned some of this in grade 10, and now we've reviewed it for grade 11. Next, we're going to take a look at some of the theory behind acids and bases. So the acid-base theory that we focus on is called the Arrhenius theory, after the gentleman who came up with this theory. This theory is commonly used for strong acids and strong bases. It works really well for strong acids and bases, and we'll go over what that means in a few minutes. So in this theory, they define acids and bases two different ways. First, what is an acid? An acid is a substance that produces hydrogen ions when dissolved in water. So anything that generates hydrogen ions when you mix it with water is considered an acid. Remember, acids need to have the AQ beside them, so they're aqueous. And acids always start with hydrogen at the front of the name for the ones at least that we've seen so far. Since we're talking about acids and bases in this unit, your nomenclature with acids comes back quite a bit as well. So if you think you need to do a review of that one, that would be something I recommend. So as an example, if we showed that with an equation with some ions, what happens when we take hydrochloric acid and dissolve it in water? Hydrochloric acid is going to break apart into its two ions. It's made up of hydrogen ions and chloride ions. In solution in water, you get hydrogen ions and the chloride ions. And because you get this being produced, this makes your solution acidic. Next, let's take a look at the definition for a base. So a base also produces an ion when dissolved in water, but it's a different one. A base is a substance that produces hydroxide ions when dissolved in water. We've seen hydroxide compounds before, but make sure that they're dissolved in water here. So here's an example. Sodium hydroxide, it's going to break apart into its two ions in water, sodium ions and hydroxide ions. So here's your positive sodium ion, and here's that negative hydroxide ion. That ion makes something basic. So this theory talks about how a substance behaves like an acid or a base by producing a particular ion in solution. There is another theory called the Bronsted-Lowry theory that deals with other types of acids and bases, but that's more covered in grade 12. So you may read a little bit about it, but grade 12 is when you'll see a lot more about that. Next, we're going to move on and briefly talk about what makes something a strong acid or base or a weak acid or base. You might hear those terms and not really know what they mean. They both can be harmful to you, and the name is a little bit deceiving because strong doesn't mean worse, it just means it behaves differently when it's dissolved in solution. So let's take a look first at what does it mean to be a strong acid or a strong base. So when you put a strong acid or a strong base in water, it completely dissociates. That means 100% into its ions in water. So all of the acid or base molecule breaks apart 100% into its ions. So if we were looking at something like hydrochloric acid, which is an example of a strong acid, when you take this acid molecule, 100% of it breaks apart into ions. So as it gets dissolved, you only see these two ions present in solution. The same thing would happen with a strong base. So a strong base would 100% break apart into its ions, a positive ion and the hydroxide ion, and you wouldn't have any base molecules left over at all. So what are some common strong acids or strong bases? So let's take a look at a list together. Now there's a lot going on here, so don't worry. But there are 6 common strong acids that you should be familiar with. The 6 common strong acids are hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, and perchloric acid. These are ones that are common acids that you see in our level of chemistry. Of course, there are other strong acids. We won't be working with them though, however. So these ones all will break apart into their ions in solutions. All of them have the hydrogen ion. So the hydrogen ion will break apart and you'll have chloride ions or bromide ions or iodide ions, nitrate ions, sulfate ions, or perchlorate ions in solution. None of these molecules are left. What are some examples of strong bases? These are some common strong bases. This isn't a full list of them, but these are ones that you might see. Sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide. But really, for the most part, most of the metals in group 1 and group 2 on the periodic table, those are your alkali and alkaline earth metals. If they combine with a hydroxide ion, they form strong bases. So it's not just limited to these 5 that are here. If you combine them with other metals in those first 2 columns on the periodic table, you could consider them to be strong as well. For contrast, what does it mean to be a weak acid or a weak base? These ones behave a little bit differently in solution. Weak acids and weak bases only partially dissociate into their ions in water. So that means not all of the acid molecule or base molecule will break apart into its ions in solution. So less than 100%. So you could have a little bit of the acid molecule and the hydrogen ion and whatever negative ion there is. This is an example of a weak acid. This is acetic acid. And so when acetic acid dissolves in water, it's going to produce some hydrogen ions. It's going to produce some acetate ions, but you're going to be left also with some acid molecules in the solution. So you have a little bit of the acid molecule, you have some of the hydrogen ion, and you have some of the acetate ion present. A little bit of everything is present. Because there's a little bit of everything present, they behave differently and they set themselves up in something called an equilibrium, which means it's a process where you have some of the ions form, then they reform to give you your acid molecule, and it goes back and forth. It uses a special arrow. It's a half arrow in the forward direction and a half arrow in the reverse. This is called an equilibrium arrow. For now, we just need to know the difference between a strong acid or a strong base, but there's a lot more that comes in grade 12 with this. And to deal with the fact that there's a little bit of a different situation happening on that chemical level, you have to learn another acid-base theory to deal with them properly. So this one, to explain this type of theory, you would have to learn something called Bronsted-Lowry. But that's more for grade 12. So for now, just be familiar with the difference between strong acid and strong base and weak acid and weak base. And more will be covered later on. In terms of their pH, you can still have weak acids and weak bases with really low or high pH. And same with strong acids and strong bases. It really just depends on how concentrated your solution is there. Now what we're going to do is move on and look at the pH scale in a lot more detail and try out some more calculations. So you may be familiar with the pH scale from grade 10, but let's take a look at it in some more detail. So what you might remember about the pH scale, it looks something like this. It goes from 0 to 14. In the middle is 7. We know 7 is neutral. Less than 7, you have your acids. Above 7 up to 14 is basic. pH stands for the power of hydrogen. So this scale actually measures how many hydrogen ions are present in solution. Down here or closer to 0, you have most acidic. And up here you have most basic. What you may not have known, however, about the pH scale is it's based on a logarithmic scale with a base of 10. So it goes from 0 to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So this is our whole pH scale. Anytime you're jumping between, you're dealing with a factor of 10. Every time you jump between one interval on the pH scale, it jumps by a factor of 10. So this is based on a logarithmic scale. So if we were dealing with, let's say, starting at 7 with neutral, because we could do this with acids, and every time we jumped down 1 point on the pH scale, we know down at 0 is most acidic and here is neutral, so not acidic at all. So every time we go down, if we drop from 7 to 6, the solution gets 10 times more acidic. When we go from 6 to 5, it gets 10 times more acidic. When we go 5 to 4, it gets 10 times more acidic, and so on. You can see every time that happens, you're going to increase by a factor of 10 in terms of acidity. The same would happen if you were going the other way in terms of bases, but because this is dealing with just the concentration of hydrogen ions, it would decrease its basicity by a factor of 10 and increase acidity by a factor of 10. We don't need to worry too much more about the math though. What we're going to use it for is dealing with calculating, and how we're going to do calculations are looking at the hydrogen ion concentration, and it's going to be calculated in moles per liter. That's how we measure this scale in dealing with the logarithms or factors of 10. So all of the values are also based on moles per liter and the concentration of hydrogen ions. So what we're going to do before we try out some calculations are just compare concentration of hydrogen ions versus hydroxide ions, and what the pH would be at 25 degrees Celsius, so at room temperature conditions. If you're dealing with acidic solution in terms of hydrogen ion concentration, it's going to end up having a hydrogen ion concentration greater than 1 times 10 to the negative 7. That means we've got more hydrogen ions compared to hydroxide ions, and when we calculate pH, it's going to be less than 7. Our neutral solution will have a concentration of hydrogen ions equal to 1 times 10 to the negative 7. It's equal to the number of hydroxide ions. Hydrogen and hydroxide, they cancel each other out because the concentrations are equal, and you get 7. Think hydrogen and hydroxide would combine together to give you water, and we know the pH of water should be neutral at 7. Basic solutions will have concentrations of hydrogen ions less than 1 times 10 to the negative 7, very small. And we may compare hydrogen versus hydroxide in solution, they'll have more hydroxide ions. In terms of calculating pH, what that does is make a pH value greater than 7. So how do we actually do any calculations with pH? There are a set of formulas that we need to be familiar with. So let's take a look at these. So here are acid-base formulas. First, you see a whole bunch of square brackets being used here. If you see square brackets, it's referring to moles per liter. You might have noticed also in some of your homework, sometimes molarity or moles per liter. Instead of writing moles per liter, you can write a capital M with the number. That stands for molarity. You can do this here as well. So if you don't have your calculator handy, I would recommend grabbing it and taking a look, because we're going to look for that log button on it. You may have used it in math, but if not, we're just using it very straightforward here in terms of calculating pH. So if we want to calculate the pH of a substance, what we have to do is find the hydrogen ion concentration in moles per liter, and we're going to plug it in our calculator. And we do that by putting a negative sign, hitting the log button, and often on a lot of calculators, you need to put the brackets around the value that goes into log just to make sure that it works properly. And then when you enter it, you get your pH value. Conversely, what if you want to find the hydrogen ion concentration? You can do this if you have the pH. You're going to take a base of 10 and raise it to the negative exponent of the pH. So 10 negative pH as an exponent. There's also another scale, which isn't as commonly used, but it's called the Poh scale. It measures the strength of acids and bases based on hydroxide ions. If you run into that one, the formula ends up working the same way. If you're ever asked to find the POH, the power of hydrogen ions in a solution, you're going to use negative log again, but you need to put the hydroxide ions in there instead. You can also find hydroxide ion concentration by taking 10 to the negative POH. So these formulas are identical, except one is measuring the strength of hydrogen ions and one is measuring the strength of hydroxide ions. Both of these are directly related to one another. If you took the pH and POH and add them together, it always adds up to 14. So both scales are based on 14. Or you can take the concentration of hydrogen ions and hydroxide ions, and they will equal to 1 times 10 to the negative 14, provided you're still at room temperature conditions. So any of these formulas can help you answer some of the questions that we'll see going forward. So let's try out a formula to make sure, a problem, so you make sure you get to use these formulas and see if you can use them well on your calculator. So what if you just want to calculate pH? Calculate the pH of a solution with hydrogen ion concentration of 0.0038 moles per liter. So if our hydrogen ion concentration is 0.00380 moles per liter, and I want to find the pH, I'm going to have to go and look at one of my formulas. So if we take a look up here, if I have my hydrogen ion concentration and I want to find pH, I can go right away and use my first pH formula. So let's go ahead and try that. pH is going to be negative log and put in hydrogen ions in there. And I want you to try this in your calculator just to make sure you've got the right hang of it. And plug that in your calculator and see what you get. If you're doing this properly and have everything set up on your calculator, it should be 2.42. Now you're probably thinking, wait a minute, what about significant digits? When we report pH or POH, the standard is always to keep 2 decimal places, regardless of what significant digits tell us. So make a little note somewhere when you're reporting pH, POH, whatever it is, always use 2 decimal places. So some calculations can be straightforward. Just use one formula, plug it in, and get your answer like this. Let's try out another one together. Tomatoes have a pH of 4.2, and let's just add a 0 in there because we should have 2 decimal places. What is the concentration of hydrogen ions? So pH 4.20. I want to find my hydrogen ion concentration. So if I go and take a look at my formulas, I should be able to find one that has hydrogen ions as what I need to solve for and pH. You should find you can try this one. Concentration of hydrogen ions is 10 to the negative pH. So again, pause the video, punch this in your calculator, see if you can get the right answer, and here you're going to round as well to significant digits. So when we check our answer, it should be 10 to the negative 4.20 as an exponent. And when we round it here, we want 3 significant digits for 3 significant digits up here. So you should get 6.31 times 10 to the negative 5. And our concentration is moles per liter. Okay. Now the first 2 questions are only one step. Now we're going to try out some problems that are a little bit more challenging. So let's look at question 3. A solution has a pH of 11.18. What is the hydroxide ion concentration? So let's write down what we have because this is always helpful. Now, when you look at the 2 pieces of information that are given in this question, you have 1, pH. This is dealing with hydrogen ions. And 2, we have to find out something with hydroxide ions. Here we've got 2 different ions. If you have 2 different ions, chances are you're probably going to have to use 2 of the formulas that are given to you on the previous part of the lesson. So there's 2 ways you can solve this problem. So if you think you know what you want to do, or to try out a couple of the formulas, flip back and take a look, pause the video, and see if you can try them. And then I'll show you both ways that you could calculate using different formulas. So hopefully you gave this a try. I'm going to walk you through one and then show you the answer to the other. So one option could be, since I'm starting off with pH, I could use my pH plus POH formula to change my value in terms of hydroxide ions. So this is hydrogen, this is hydroxide, but it's not hydroxide ion concentration yet. I'll need to use another one afterwards, but it's a good starting point. So POH is going to be 14 minus pH, which means 14 minus 11.18. And when I do my calculation, I should get 2.82. This is POH. So now that I have POH, how can I change POH into hydroxide ion concentration? Well, we've got a formula for that. 10 to the power of negative POH. So that one I can definitely do. So I take my power of 10, negative 2.82. And then here, when I plug that in, I'm going to get 1.514 approximately times 10 to the negative 3. And this is moles per liter. So this is one way that I could calculate. The 2 formulas that I used are my pH plus POH is equal to 14 and my hydroxide ion concentration over here. Now, you may have solved this problem a different way, and I'll show you the answer to another approach you could use. You may have solved it using these steps. So maybe you started off by saying, well, I'm going to take my pH and I'm going to convert it into hydrogen ions. You can definitely do that. You take 10 to the negative pH and you should get about 6.6 times 10 to the negative 12 moles per liter. Then you can use the other formula that relates hydroxide and hydrogen, where they both equal to 1 times 10 to the negative 14. And when you rearrange that, you'll end up getting the same answer here, about 1.51, and I forgot the 4, times 10 to the negative 3 moles per liter. So either way will get you to your answer, and often there's more than one way to solve the problem if you have to do two different conversions with hydrogen and hydroxide. Doesn't matter which one you do as long as you tried both. Or sorry, I tried one, then you'll be able to answer the question. Now let's try out another problem, and this one's going to involve a little bit of stoichiometry and the pH formulas that we've been working on. So you have 0.34 grams of hydrogen sulfate dissolved in 230 milliliters of water to make a solution of sulfuric acid. What's its pH? First thing we need is the formula for sulfuric acid. Hydrogen sulfate is the solid, but when we dissolve it in water, we get sulfuric acid. So sulfuric acid is H2SO4 with the aqueous. So here we're dealing with a question about sulfuric acid. We're given a mass and a volume, and we want to find pH. So we need to think, well, what happens to sulfuric acid when it dissolves in water? This is a strong acid. It's one of those 6 acids on our strong acid list. So in water, when it dissolves in that 230 mils of water, we're going to get hydrogen ions and sulfate ions. But here, remember, there's 2 hydrogens. So when I write out my equation here, I've got 2 hydrogen ions, and then I've got 1 sulfate ion. So what I'm starting off with is a mass of 0.34 grams, and I've got a volume of 230 milliliters of water, and I want to find the pH. Now, when I think of pH, that means I need to find hydrogen ion concentration. When I look at my equation here, here's my hydrogen ion concentration. So if I'm solving for pH, that means I need the concentration of hydrogen ions. That's really what I need to get to before I can get to pH. So how do I do this? Well, if we think back to stoichiometry and some of those ion concentration problems that we've already tackled, most of it, except for that last step, finding pH, is exactly the same as one of those questions. Here I have a mass and I have a volume for my sulfuric acid. The volume I'll need later on when I deal with concentration, but I can change my mass into moles. So the first thing I'm going to do is find out how many moles of sulfuric acid I have. And I can do that using my mass and my molar mass of the sulfuric acid, 2 hydrogens and 1 sulfate ion. Once I have that, then I'm going to find out my moles of hydrogen ions. This is going to be your second step. How do I do this? Mole ratio. I can see up here I've got 1 mole of sulfuric acid for 2 moles of hydrogen ions. Then I can find my concentration of hydrogen ions. I'm going to make this just a bit more clear for us. I think that's a little bit better. And remember, to find that out, I can use my C is equal to N over V. And my volume I have is that number here. Once I do that, then I can go over here and find my pH. That's going to be step 4. So I think that since we've already covered ion concentration problems, you should probably be okay now that we've mapped this out in the steps that we need to for you to try. So I would like you to try and pause the video and see if you can try and solve as much of this problem as you can, and then we'll walk through each of the steps together. So now what we'll do is start walking through those steps together. We'll look first at step 1 and step 2. So step 1, I have to convert my mass of sulfuric acid into moles. So I'm going to divide it by my molar mass of my sulfuric acid, and you should get about 3.47 times 10 to the negative 3 moles. This is for my acid. Then step 2, I need to do my mole ratio. It's a 2-to-1 ratio. So I have 2 moles of hydrogen ions for every 1 mole of acid. My moles of acid cancel, and I'm left with moles of hydrogen ions. So twice as many. And when you look at that ratio, you know we have to double it. Now I'm going to take this number of moles of hydrogen ions and plug it into my concentration formula. C is equal to N over V. When I do that, here's my moles that I just calculated. I divide it by my volume, and I get about 0.0301 moles per liter of hydrogen ions. Now that I have my concentration of hydrogen ions, this number here, then I can plug that into my pH formula. My pH formula is negative log of hydrogen ions in moles per liter. So when I do that, pH is equal to negative log of hydrogen ions. When I round it to 2 decimal places, I get a pH of approximately 1.52. So even though some of these questions are initially asking something different, it might be pH, it might be POH, or a concentration of hydrogen ions or hydroxide ions, most of the steps and concepts are things that relate back to solution stoichiometry and often involve some kind of ion concentration. So think back to those problems to help you solve. Okay, now if you're up for a challenge, and this is an optional extension question, if you want to challenge yourself to see, have I been learning all that I need to know about solution stoichiometry, this question puts a lot of different things together. So if you want to try this one, we'll walk through the answers together. We want to take a solution of calcium hydroxide, and it was made by dissolving 0.25 grams in 250 milliliters of water. Then 42 milliliters of the solution was diluted with water to a total volume of 320 milliliters. And then we want to find out what's the pH of this diluted solution. So, 2 different things going on here. One, you are making a solution of calcium hydroxide. And then 2, you're diluting your solution. And then 3, you're measuring the pH. This is the process of what's going on. So in the first step, you need to find out what the concentration of your solution is, then what it is diluted, and then what is the actual pH. So if you want to try this out, if this helps you kind of get started, you can pause and get started. If you're not really sure quite what that means, stay on the video and we'll break it down into a few more steps to help you get started. Okay, so if we have calcium hydroxide, When it breaks apart into its ions in solution, you get calcium ions and hydroxide ions. So, in the first part of the question, if we want to find out what's going on, we need the concentration of solution. So, we are given 0.25 grams, and it's dissolved in 250 milliliters of water. We know at the very end of the question we need pH, and pH, remember, is negative log of hydrogen ions. We don't have hydrogen ions here at all. We have hydroxide ions. But we do have some formulas that convert hydroxide ions into hydrogen ions. So to get to pH, what we really need is the concentration of hydroxide ions. So in step 1, making your solution, what you need to do is find out what's my concentration of hydroxide ions, undiluted. And this is going to be similar to the previous problem. It's a stoichiometry problem. So for step 1, find the moles of calcium hydroxide, change them to moles of hydroxide ions, and then into concentration of hydroxide ions. Mole ratio step, and we know our formula for concentration. This will deal with step 1. Once you deal with step 1, then you have to do step 2, dilute it. So step 2, your dilution, remember your dilution formula, C1V1 is equal to C2V2. Your C1 is going to be determined by step 1. You have your initial volume here. You're taking 42 milliliters of that solution. Your V2 in the question, it says you're diluting it to a total volume of 320 milliliters. And this is what you're trying to find. This will give you your concentration of hydroxide ions diluted. Once you have that, once you have your diluted formula, then you can find your pH. But you're going to need 2 pH formulas to get you there. So, if that helps you get started, if you are taking on this challenge, pause the video and see how you do, and we'll walk through those steps next together. So, for step 1, it was trying to find the concentration of hydroxide ions, and I've combined this together in a unit analysis answer, but if you didn't do this, you don't have to. The first step here, this is finding your concentration of, your moles of calcium hydroxide. 0.25 grams divided by the molar mass of calcium hydroxide, and we get moles of calcium hydroxide. Those cancel out. Then step 2 was do my mole ratio, 2 moles of hydroxide for 1 mole of calcium. And then here, this was my concentration. C is equal to N over V. If I look at my units, how they cancel, I have moles of hydroxide. It'll be in the numerator divided by my volume. So you should have got an answer of about 0.02699 moles per liter in terms of hydroxide ion concentration. Whether you did this all together in one step or broke it into 3 steps, you should still get this answer. Then comes the dilution part. So this is the concentration of hydroxide ions undiluted. Then we dilute it. So, as we labeled before, this is our concentration. We're given how much of that concentrated solution we take, 42 milliliters. We want to find the concentration of our diluted solution, and this is our 320 milliliters. You could have left both volumes as well in milliliters, and it still would give you the same answer. So when we take a look at our dilution formula and plug in the numbers, this is our formula rearranged. C1V1 over V2. I'm going to plug in those values from up above. And I should get 3.54 times 10 to the negative 3 moles per liter of hydroxide ions. This was step 2, part 2. Now that I have that, I can go and use my pH formulas to try and find out pH. But since I'm dealing with hydroxide, I need to first use one of the hydroxide formulas to help me get to pH. So again, there's 2 ways you could have done this part of the question. I decided to go with POH. So POH is equal to negative log of 3.54 times 10 to the negative 3. This is going to give me 2.45. Then I plug it into my pH formula here. This one here, remember, is pH plus POH is equal to 14. So it's been, just for reference, rearranged. So 14 minus POH, and we end up with a pH of 11.55. So don't worry if this question seemed really overwhelming. It's tricky and combined many concepts that you've seen so far in this unit. But if you took on the challenge and tried it out and were successful, you're doing great. If you need to do some practice first and then want to come back and try this question later, after you've practiced throughout the next little while, this is also a good test to see, do I know what I'm really doing? Can I put some concepts together and understand what's going on? So if you want to try it out later on, that would also be a good way to test your knowledge.